Okay, so good evening, everybody. It's my pleasure to introduce Rich Rademacher, who's an electronics engineer from Stevensville, Michigan, USA, with more than 20 years of experience in embedded systems, digital signal processing, and communications engineering. He began engineering work in high school, working on PLC controllers for industrial robotics, and as a concert audio engineer. He was an embedded systems engineer for Crown Audio and lead DSP engineer for Aerostream Communications, making software-defined radios. He spent 9 years active duty in the US Air Force, where he worked various research programs for jet engine development, intelligence, radar, and scientific data support teams in Ohio and Florida. Most recently, his interests are in quantum computing, working at the Iron Trap Computing Group at the University of Waterloo in Canada and Q Control Sydney. Rich has a BSEE from Michigan Tech in DSP and MSEE in radar signal processing from the Air Force Institute of Technology and an MS Applied Physics and Quantum Information from the University of Waterloo. He is presently completing radio frequency FPGA work at the University of Sydney for drone fingerprinting, and he will soon be joining the University of New South Wales Silicon Qubit Research Group as a PhD student in quantum noise theory. His hobbies include pure maths, walking around Sydney, making printed circuit boards, and skydiving.
So, thanks, Philip. Thanks, everyone, for inviting me to be here. The title of this presentation is on quantum key distribution for low Earth orbit satellite communications. And this is something that I think is particularly useful for people who are amateur radio enthusiasts, because, as we'll see a little bit, radio and light are the same thing, but we're going to use them in a very different way in quantum key distribution. And if I can, oops, no, I'm a little fast on the draw there. So what we'll just talk about quickly is, I apologize, I hope everyone can read that. The scope of this talk, we're going to talk a little bit about security and encryption, just to set the stage. Most people know a lot of this stuff. I will talk a little bit about the quantum properties of light, because they are so important to what we, to the way that this will work. We'll talk about the quantum key distribution equipment that you'll see in a laboratory or in a piece of equipment. And we will talk about the specific quantum key distribution algorithm called BB84, and some very exciting results in just the last 5 years or so in actual systems that are actually using this in orbit and on the ground right today. The time for this is about 40 minutes. If we need to take a break, someone just let me know. Sometimes I forget where I am and stuff like that as we're talking about exciting topics. So the scope of this is quantum key distribution for satellite. And what we really mean is that there is a ground station somewhere and a good satellite up here in orbit shadowed by a bad satellite. Bad satellite can be an eavesdropper, and we do not want information to be stolen from us. Now, obviously, that's a pretty good chance for encryption. Okay? Quantum key distribution, the main topic of this, is basically moving a small amount of data in a way that cannot be eavesdropped at all. Unlike encryption, which is hiding the information, this prevents eavesdropping altogether. We will use a quantum channel, which in this case will be light in a quantum mode, for the critical information as we get the encryption key up to the satellite and the satellite coming back down. We'll use what in the business we call a classical channel, which is just a regular communication channel. No quantum involved. This could be BPSK, could be KU band, it could be anything that you'd like. But this is capable of being eavesdropped, and it is public, meaning that we are okay with someone listening into the classical channel. And we use this channel for coordinating the quantum operations. So that's quantum key distribution. To set the stage a little bit, because the word quantum gets thrown around a lot, and to make sure we understand exactly sort of what this talk will really be about, we'll talk about what it's not very quickly. Okay? This is not going to talk about quantum computing, which is the special algorithms that have speed up that also use quantum effects. These can do kinds of calculations that are either difficult or impossible in other computers. That's another topic for maybe a different day. We won't really talk much about encryption that's quantum safe, which is to say those algorithms that are resistant to these quantum attacks. Those are very advanced, and it's a very exciting topic that's changing right away, but a little bit too much for one day. There's also, you'll hear the word quantum sensing, which is when we use quantum effects for precise measurement, like atomic clocks, or the measurement of gravity, so that we can see time slow down as we move 2 meters off the ground versus not. That's a quantum sensing operation. And the word quantum teleportation is actually part of quantum key distribution, but we're not going to talk about that particular protocol today because it would kind of be like 10 more slides to get that set up. So instead, we'll talk about a specific quantum key distribution system called BB84. And this one is particularly straightforward for those of you in the radio community who are familiar with microwave radio frequency engineering, such as polarization, circular linear polarization, C-band, X-band, Ku-band, S-band, those kinds of things that you would probably have if you haven't had the joy of experiencing microwave engineering. It's of course a lot of fun. So let's start off with just laying the base work for security and encryption in general. Right? And this is a basic model of an unsecure channel that we would like to do. This is our link between the ground and the satellite, the bird up in the sky. And the idea is we have two actors, Alice and Bob, A and B. By the way, in case you get confused, Alice has the bow on top of her head, and Bob has the bow in the bow tie. Okay? Alice and Bob are the good guys. They want to share information. Alice wants to tell her PIN number to Bob through some channel, some radio frequency channel or optical channel, doesn't really matter. However, there is an eavesdropper named Eve who can listen into everything, and Eve is infinitely patient. Eve is has infinite resources. Eve has seen your browser history for the entirety of your life. Eve can compute things that neither of these two can't. The only thing Eve cannot do in this model is she cannot see the information before it gets transmitted. She's not a hacker. Okay? So she can't break into the computer, but as soon as it's in the airwaves, she's been watching you your entire life, everything you've ever sent. If we send that 007 PIN number in plain text, Eve gets it and now has a copy of it and now can steal all of your bank accounts. Instead, we would rather they encode their information. Alice encodes her information in some way, and Bob decodes whatever they get, and they share it through that same channel. And the name for this would be called the ciphertext. The encoding might not be known to Eve. Remember, she has infinite resources, so maybe she could figure it out, but she didn't know what it was if they didn't say it ever. And this encryption is fairly well understood. We use it every single day. She gets a message that's just all garbled rather than my PIN is 007. So that's our basic unsecured channel. Now, encryption is something we've all heard the word and stuff like that, but again, just to set the stage, a simple encryption scheme could be to just take every letter in the alphabet and move it to another letter. Every time you see an A, make it an F. Every time you see a B, make it a C. This is called monoalphabetic substitution. It's very simple. Many of us have played this game when we were kids. It's sometimes called the Caesar cipher, I believe. And the idea, right, we have an alphabet, an exhaustive alphabet. We take all the letters and we scramble them up. This scrambling, in this case, was just simply me typing it in on the keyboard. And the result is my PIN is 007 becomes this string of garbage, right? Monoalphabetic substitution. Simple, has some problems. We'll see those problems in just a minute. A bit of a more advanced scheme, well, in fact, a perfect scheme, is called the one-time pad. And the idea is that Alice or Bob, either one, generates a big table of random numbers. Completely random, no pattern to them whatsoever. You could take a diode and a microphone and just measure noise and call that the thing. They create two copies of these random sequences and they share them to each other. Bob's got a book and Alice has a book. All right? And then every message every letter in the message, we add the next letter in the random pad. First letter goes to M, and it is added to it. So my random number 27, I had 27 to M. Next the number 54, I had 54 to Y. If I ever reach the end of the alphabet, I just wrap back around again. Okay? And so for every letter, we just add the next random letter. And then we take this result and we send that out. The key to this is we never reuse a random number. In fact, you could just burn off the letter or take a Sharpie. Every time you use a letter, first letter, struck it off the pad. Never used again. Now, in order to decode this, all Bob has to do, because he's got the same pad, is subtract that letter back off, right? First letter 27, whatever M plus 27 was, I got that letter. I'm going to subtract 27 off, I get a M again. Next one, 42 or whatever I said, I get a Y. And so he can piecewise pull this apart. This is a perfect scheme from an information theory perspective. This will work every single time. A bit more of an advanced scheme, which is something that we use more, is to think about it a little bit mathematically. And I will pause to say that we will try to keep the maths to a minimum on this, but there are two different mathematical equations that will show up, and this is not one of the interesting ones. Okay? But the idea is we use what's called a permutation. A permutation is just simply what we said before. Take the letters, scramble them. The same number of letters comes in, the same number of letters comes out. The letters are only used once, and therefore we can move them back again. Same thing with the one-time pad. First letter, first number. Second letter, second number. So there's a scrambling that goes on there, right? And the idea for a permutation is that there's always a reverse. So whatever scrambling we do, there has to be an inverse to it, which means we can never reuse. Two things can't be the letter A, for example, right? We could draw this a little bit better and just say, from a way a mathematician might look at it, say the ciphertext is P, this permutation thing, applied to the message. And the plain text is the inverse, the reverse, applied to the ciphertext. And that means we have this relation that says the inverse applied to the scrambler is 1, or does nothing. So P does it, P inverse undoes it. Simple, basic things, right? A better thing is to say, well, maybe there's not one P. There's lots of scramblers, right? And in fact, we're going to give them a little name. This is scrambler number 1, scrambler number 2, scrambler number 3. And we'll call that name the key. And so we'll just simply say, okay, I'm going to put K's at the bottom. The P with the key, and the P with another key, and the P with another key. Then we add one new condition right here that says unscrambling using key number 1 and scrambling with key number 2 is not 1. What do we mean by that? If you descramble by the wrong key, you get garbage. Okay? So simple. 1 means you got back what you started. Anything not 1 means garbage. You use the wrong key. Right? Basic stuff. No problem. Now we talked about the substitution cipher, and now we'll get a chance to see why this doesn't work. What you are seeing here is a count of all of the letters of the text of the novel A Tale of Two Cities by Charles Dickens. I actually just downloaded it, and I applied a substitution cipher. I just created ABCD, and I made a new random sequence, and look what it is, right? So this is the true thing, the frequency of letters. And you see some interesting things. I hope you guys can see this. If not, for anyone in the back, what we have down here is the characters of the alphabet in order. Here's the capital letters, and then here's the lowercase letters. And you notice one thing is very, very frequent, and that's the space bar, right? Also, over here is some unprintable letters. That's the carriage return, and the tab key kind of ended up at the bottom somewhere. But most of the letters are the lowercase numbers up here. And they occur with high frequency. The letter A occurs a lot. The letter E occurs a lot. If you guys have ever watched the TV show Wheel of Fortune, at the end, they say, you know, guess the letters of this phrase and win a car or something like that. But they'll give you, at the final round, the most common letters. R-S-T-L-N-E. And that's exactly what the highest peaks are, R-S-T-L-N-E. Great, so we've just learned a whole bunch about A Tale of Two Cities. You can do this with the Bible, you can do this with Shakespeare, you can do anything that you want, and you'll find this pattern occurs about the same way every time. No matter what the text, E is the most common vowel. In fact, E is the most common letter. The space bar is almost always the most common non-printable character and stuff. Which means if I take my scrambled data and I look at it again, I will see those same peaks just in different positions. So I can just say, where's the highest one? I know that's the space bar. Well, where's the highest one? Oh, look, it's this greater than. What's the next highest one? Oh, it's the hashtag right here, the pound sign, right? Okay, so I've now decoded 2 letters, and I can go through this process and get really good guesses. All right, so that's why we don't like the Caesar cipher, the substitution thing that we played as a kid. It's very easy to break this, especially the more you talk, right? So the more you say, the easier it is to build up these statistics. Now, if I do the same thing with the one-time pad, I get a new thing. You notice same frequency up here, but it's been spread out. Why? Because in the first case, A was always mapped to the same letter. Every A was always the same F. Therefore, all the A's turn into all the F's, and all the G's turn into Q's, or whatever like that. In the one-time pad, the key was I never reused the same character twice, the same scrambler twice. So now the first A might be a G, but the second time it sees an A, it might be a Q. So A's keep getting spread around, right? So this is much, much better. And the point of this whole thing is I've taken things that have a lot of information. Eve can find this out, right? She could look at this thing, and she could look before at what Alice had sent and say, okay, I can solve it. She can, and she's got computing power to do this, and heck, we can do it on paper if we need to. But this here is a much harder problem because what you've done is you've reduced everything to the same likelihood. Every character is equally likely to be every other character. And this will be the key to all good encryption systems, is turning something that's not very random into completely random. Now, Eve is no better off than just flipping a coin or randomly guessing. It's the same thing. There's really not any good choice to anything. So that is the key to a good encryption system, is turn everything into randomness. It's no better than just guessing. But anytime you can get some side information to help you out, you beat the system. Okay, now one thing that you've seen a lot or heard a lot probably in the news and stuff like that, and you use it every day in your computer, is called public key cryptography. And this is not going to be a particularly intensive subject on that. But the one-time ad was perfect, but it's huge, right? I need the same size pad for the same size data. If I need to send a 200 megabyte wave file, I need a 200 megabyte pad. And there's no way that I can shrink it because it was truly random. Can't shrink the randomness. Bob would lose out on, he wouldn't know what to do with it, right? So, and the pads can't be reused. Plus, this important thing, you still have to get the pads to Alice and Bob. Someone has to deliver those pads to them. If I'm a spy, someone's got to show up at my house with a new pad. Or I got to take it with me and hope I don't get stopped at the airport, right? So we don't like that. Okay? So cryptography algorithms are attempt to use a small key. But in the purest sense, the pad in the one-time pad was the key. It was just a bajillion digits long. So we want smaller things, right? That's a good crypto system. The idea of a modern public key system is this, and don't worry about this math. This is more of an example of how this is done, not really for retention. But basically what we do is we treat the message like it's a very long number. If it's 1,000,000 characters long, like Tale of Two Cities or something like that, then it's a 1,000,000-digit number. And I'm going to multiply it by a big number. And then I'm going to take the remainder of a big number and use that as the remainder of another thing. And that turns out to make a really good key system. The point of this was not to get too much into cryptography. It's more to say we still, with all these powerful things, need to exchange the keys. Somehow the key needs to get to Alice and Bob. Right? Anyone who's interested, by the way, in the details of the public key system, this is a link, and I'll make sure that you guys have the slides with the links on them and stuff from a channel on YouTube called Number Files, a bunch of mathematicians who really go into this well. Now, one last thing before we're done with cryptography is to talk about public key infrastructure. And what that means is trying to solve this thing of how do you share the keys around, okay? PKI, we call it. The first question is, how do we trust a new person? A new person, I go to a new website, I've never been there before, it's a new bank. How do I know that it's the bank, right? Are the person I'm talking to, are they who they claim to be? This is called authentication. Are they actually who they say, or did I start talking to Alice and Bob and suddenly Eve has impersonated one of them? Is the key a bad key? Has it been compromised, faked? It doesn't encrypt anymore, or Eve already knows it. She somehow got it through rooting around your home or something like that. Am I talking to a chatbot? If anyone's recently had in that, you know. And finally, is the NSA listening in on my whole conversation? It is at this point where I will unveil the first of 2 jokes that are built into this, because as luck would have it, I happen to have an NSA-sponsored T-shirt, thus showing that they're breaking into everything, including clothing.
Is it bugged?
It is. It's actually got a bug clipped right onto it right now, right? So the idea, though, of public key infrastructure is to try to answer many of these questions, right? It's not an encryption system. It's a way of authenticating trust, okay? The chain of trust that we're talking about between Alice and Bob in this hypothetical example, we still haven't gotten to quantum yet, right? But we're just getting background, is as follows. If Alice wants to talk to Bob through a web browser, whether Bob's a website or just a person, whatever, first her browser has to decide on someone to hold all the keys. This is called a root key authority, and there are a couple of companies, DigiCert or whatever. If you've ever bought a website with an HTTPS on it, you have paid money to one of these people to have them vet you. Okay? But the browser trusts these authorities. Alice's browser has several of them pre-installed. When you get a new copy of a laptop or you install a new version of Chrome or Edge or Safari, whatever you want to do, these root keys, the first keys get installed. So we have found our first point of how do we get the keys. The answer is when you load your browser, some keys are pre-installed. The certificate authority, the credential authority, has verified Bob in somehow. He paid his money, he gave his driver's license or whatever it was, and checked his bank account for the extra 1 cent that they give you or whatever it is to verify he is who he says he is. Once the key authority trusts Bob, Bob can present a certificate with his key to the browser, to Alice's browser, right? Since Alice trusts the browser, and the browser trusts the authority, then Alice trusts Bob. And that is the completed chain. By using this intermediary, the key authority, you can broker trust. Alice trusts the browser trusts the key authority, and the key authority trusts Bob. Therefore, Alice can trust Bob. Okay? But again, we have this same limitation. How do those original keys come in? Remember, Eve is infinitely patient. If she compromises one, she's got you forever. Who loads that very first key? And how do you compromise a key? Now, on your laptop computer or whatever, you just reinstall it, there are services. What about in a satellite? Service calls are not easy to do in space. This gives us to the purpose of why quantum key distribution is so important in satellites. Okay? So with that, the next topic that we'll talk about is this quantum stuff. All right? And we're just going to talk very briefly on basic quantum properties of light. I'm going to try to keep this very, very simple. Okay? And I want to keep it not simple, not because it's not a fascinating subject, but because we want to keep it grounded in radio stuff. So, light and photons. Radio people and optics people believe electromagnetic radiation is a wave. That's the view that we take on this. Here's a plane wave equation where we have some electric field. The magnetic field is not really important, but you know how it goes. It has a polarization, and that's something that we're going to talk quite a bit about. Some intensity, E, and then some wave propagation with some wave vector R at some frequency, omega. And we can thank James Clerk Maxwell and Heinrich Hertz for this treatment, and a few others. Photonics is the study of that exact same phenomenon, except we're not going to call it a wave anymore. Photonics comes from the quantum side of things, which has a lot of people involved, not just Maxwell. Right? The first thing that we want to do is to say the energy is quantized, meaning it only comes in discrete bundles. There's no half a photon, there's no half of a, what, and it's proportional to the frequency. The higher the frequency, the higher the energy. They come in bundles. There's only ever 1, 2, 3, 4, 5, a billion, but not 1.5 of these ever. And we can thank Einstein for that, right? But there's more. Quantum field theory gives us the second thing that says waves are quantized too. They're not just, unlike up here, where we said these waves kept moving around forever, that they are actually quantized. They only exist in certain stable states. They're very dense, and they're very small. The spacing between them is very small, but they're very fixed things. So therefore, waves come in integer bundles also. Quantum electrodynamics, which is an atomic and particle phenomenon, says that waves interact, electromagnetic waves interact with matter in a very specific way, and no quantum mechanics talk would be complete without giving due credit to Richard Feynman for that. Everybody loves Feynman. You got to have a Feynman thing if you're going to do anything, right? Once we have these three things, we can come to the conclusion that light is also a particle. And therefore, we got back to what Einstein thought all the time. But now we finally have a mathematical rigor to go with it. Whew! Thank goodness. Now, the radio side of things, to bring it back, is that light is just high-frequency radio. Anything that I can do with radio, I can do with light. Anything that I can do with light, including making lasers out of it, I can do with radio. A laser in the microwave regime is called a maser, right? It's the same thing. Everything that you can do. I can make 300 megahertz individual photons. It's hard to catch them, but they're there, right? Same rules. And we can attribute this to me. And now you've seen the second joke of the day. Now. And humble too, right? Now this particle called light has some properties. First of all, we have replaced the term intensity up here with photon number. Remember, there weren't an infinite number of amplitudes. Amplitude was just saying how many photons did I get in any one instant. 10 over 1 hour, over 1 second, whatever. 50 bajillion, fine, but that's not 50.5 bajillion, or 50 bajillion 0.5, right? So photon number is one of these properties that we can control quantum mechanically. Momentum, which is the ability for when two things hit to push back against each other, that's a property of light as well. Frequency, fortunately, that didn't change. It just has a new meaning in relation to intensity. And polarization, the P up here. This is the important one because we're going to work with this one a lot. Why? Because of all of those, only polarization has distinct values. Okay? Photon number 1, 2, 3, 4 goes on forever. It's integers. There's no halves, but it keeps going. You can just keep adding photons into it. Momentum is continuous. You can have a half a meter and a third and a quarter, whatever. And frequency, you can have as many gigahertz as you'd like, right? Fractional gigahertz and stuff. But polarization, we only have two choices, right? Horizontal vertical or left and right circular. So this is a good proxy for binary data. Okay, this is where the hazard starts. I said there was going to be a limited number of math. There are 2 slides with math because I didn't count that other one. And so brace yourself. But we're going to try to keep this to the reason why this is interesting for the quantum effects that we want so much, right? Remember, we were trying to get back to the idea that I can use some quantum-y something to do the encryption without being able to be eavesdropped, to transmit without being eavesdropped. Okay, so we need some math. Those numbers that we had before, the quantum state, the number, the phase, the frequency, the polarization, momentum, position, all those other numbers out there are all wrapped up into one little property that mathematicians will call the wave function. But really this is just it's a mathematical function. We never see what this is, by the way. We never look at it. You can graph it on paper, but that's not important. What's important is how we manipulate it. Okay? Ugh, that's ugly. But we're just going to look at polarization for a second. The state can be a linear combination of anything I can measure. And in polarization, I need 2 numbers. How much horizontal, how much vertical. Circular polarization could be done the same way, but I'm going to stick with linear because it's just simpler. Okay? And the idea is, for this one here, by the way, just out of curiosity, can anyone in the back see this? Yeah? Okay. One person says, okay. So what this is saying is my part of horizontal and my part of vertical, that 1 is on top and the 0 is on the bottom. This is a shorthand that physicists will use to say it's 100% horizontal. Okay? All of the state is held in the horizontal mode, pH. But I can have mixtures too. I can have it as a combination of horizontal and vertical at the same time. Don't worry about the square root of 2's. That was just in case anybody mathematically is looking at this later on and say, oh, you forgot the square root of 2. The point is, in this case, I've got it mixed between horizontal and vertical. So it's half horizontal, half vertical. Now, is that really what we're saying? It's not quite half horizontal and vertical. That wouldn't be the term we would use, but we would say the probability is 50-50 in this case. And also, I have a negative sign in there. I can have these things add and subtract from each other in very interesting ways. So yes, you can have phases on probabilities. It can be negative. It can have imaginary components. It can have an I and Q component if you want to think of it like a digital receiver. But the point is, we can have mixed up states like that. These are called superposition states. Now we can change these with a mathematical tool called a unitary operation. And a unitary operation isn't important. The important thing is that I can change these numbers by doing stuff. Every interaction in the world is going to be one of these unitary operators. Whether I reflect the photon, which would be a change in momentum, that's changing the direction. Whether I create a photon, that would change the count, the phase, the frequency, and the polarization, of course, right? So every single thing that you can ever do to a quantum particle is a unitary operator. This example right here, by the way, is a polarization swap. You can see the unitary is this matrix right here, but I started out with my 1, 0, which was my 100% horizontal, and when I do the maths on it, I get a 0, 1. It flipped them. This is the equivalent of someone doing a polarization rotation to a photon. That's the mathematical tool that says the same thing. So the physical things that we do to stuff can have a reference in the real world. And of course, after the measurement, the state collapses to its own measurement, meaning I may have been 50-50 before of getting it one way or the other, but after I've measured it, it is 100% going to do the same thing. Okay? So after an operation, which might have been 50% vertical and 50% horizontal, it will, if you repeat it, will always get to 100. Okay, the most important thing that helps us do our quantum work for key distribution is the no cloning theorem. The no cloning theorem is based on this idea that all these things have to be unitary, and unitary things have to do this mathematical operation. This is the second math slide, and yep, you just got to live with that. We could do more if you wanted. The important result is, remember I said unitary operations are everything we can do. There is no unitary operation that copies the state or clones it, right? Unitary things have to have this thing, which basically says if I rotate the matrix and multiply it by itself again, I get the number 1, or the equivalent of the number 1. There is no operation that copies the state. Let's just see a very dangerous, a very scary looking equation. If I had 2 photons, I could take what I did before, where I had parts of the amplitude of probability of horizontal, probability of vertical. Now I get 2 of them. So how much is horizontal, 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 vertical, vertical, horizontal, vertical, vertical? First one, second one, kind of combined together. I got 4 choices. And we'll just say that those things are A, B, C, and D. They have some numbers, but it doesn't matter what they are. What we want is some operation that would turn our A, B, C, D into an A, B, A, B. I've copied all of the first stuff right here into the second one. Okay? That's what I'd like to do. The problem is the ugliness when I try to solve this equation and I get not the number 1. Okay? So I won't bore you with the math on there. But when people say you can't copy quantum stuff, they are talking about this. Because all copies would have to be reduced to a matrix like this that violates the very first rule. If I were to violate that rule, it wasn't just something that they made up because it was hard, it would break a very important thing of probability, which is that the sum of all the probabilities is 1. There's a 100% chance of something happening. You break that rule, there's no more structure to the whole thing. So we needed that to happen. That is the no cloning thing. So take it on faith that you cannot copy a superposition state, a mixed up one like that. You can measure it, turn it back into one of the 100% choices, the pure states, the eigenstates we sometimes call them, and you can put that into another one, but you can't get the mixture. Okay? So that's lost. That phase information between part horizontal, part vertical, gone. Whew. Thank goodness. Let's look at some equipment. We're hardware people, right? So let's just look at some of the stuff you might need to make these things happen. Okay? If I can get it to work. Woo! Yeah. So, what about making photons? What do we need to make those things? Well, we can take a laser, which is a coherent source. It has a precise frequency. It has all these nice things. Makes lots of photons. Okay? When you get this view right here is the radio approach, the wave, the optics approach. When we get to the photon approach, we want to think of this as a bajillion little ones coming out in order. And because we no longer have a variable called intensity, we have one called number, we can find out the rate at which these things are emitted. Our laser pops out photons at a fast rate. But the stronger the laser, the brighter the laser, the more that they come out, which is to say more they come out faster. That means if I weaken the laser, I can eventually get down to the point where maybe I only have one photon every second. Now, this should be familiar to us in the radio world because we have a device that makes strong signals weak, and it is called an attenuator. There we go. Boom. We took a nice continuous beam, knocked it down so weak that eventually they only come out in ones. Boom, one at a time. And then we wait a bunch of time. Boom, one at a time. Okay? So this is how I can generate a single photon. Just make it so weak that it doesn't do anything but. Now there's a problem. These come out randomly. I can't predict whether they're going to come out once a second. I can know there's going to be one in a second, but not where. It's going to come out whenever it feels like, on average once a second. But a more important one is sometimes we can also get double photons. This is a probability thing. So there's also a probability that two come out. And it's rare, but it does happen. So the same amount of attenuation that was giving us one will, on occasion, give out two. This will be a problem for our quantum key distribution. Detection of photons. One of the classic ways to do it is a photomultiplier tube. It's like an imaging tube, a CRT in reverse, right? And the idea is fairly simple. A photon comes in. You've got a screen with some metal on it. It's got some weak electrons on it. They're kind of they're in the valence band, so they can move around. They're conductors, right? And eventually you hit it with an electron, and they're so weakly on there that the electron gets popped out. Just got just enough energy from that photon. Boom, it pops out. It hits a following, or it's accelerated by a screen, so just like in a CRT. Boom, hits the next plate, liberates two more photons. These two liberate four. 4 turns to 8, 8 turns to 16, and now we get a shower of this. So one little electron, one photon coming in, knocked off an electron, which then allowed this cascade to happen. So these are great. These are very low noise. The technology is very mature. They're a little fragile, though. Okay, so they don't work well in space. An avalanche photodiode is another way to do it. It's just a diode that's been reverse biased just right at the edge of the Zener region, such that if I grab one more, we've moved it straight over into the Zener region, it starts to conduct. In the case of an avalanche diode, there's a shut-off effect too. But same thing. These things were ready to go. They were charged up, they're biased, just ready to go. They just need one extra photon to give them enough energy to shower it away. These are higher noise, and they have a limited number of wavelengths, right? They're very selective. They're semiconductor devices, though, so they're very robust. Vibration, temperature, all this other good stuff. So these are good for outer space. What about changing that polarization? Remember that operator that I said we could swap things around with that scary-looking matrix, right? Well, that's a physical device, right? There's several of them, in fact. We can use a Faraday effect, which looks like this. It's basically a tube with a magnet in it. And the idea is when you put a photon through a strong magnetic field, it will slightly change the polarization. Okay, that's a external Faraday effect. These are very low noise. They are fixed, though, so they're not very programmable. But I could replace the magnet with coils, like in a speaker or something like that, and we would be good. and then we make it programmable. We could also use wave plates. This is just simply a bit of glass with two special coatings, and the coatings provide a phase rotation. These are fixed also, right? So I have to put it on a motor or something if I want to change the thing under computer control. And the LCD display, like this, probably this very projector is an LCD thing. So what is a liquid crystal display is just a polarization rotator, right? It's a long molecule that kind of has an affinity for one polarization direction or another, and if I apply a current, I can turn it on its side, so I can change the rotation of that. Right? These are a little higher noise, but they are programmable. Right? Obviously, this very projector and my laptop are using programmable electric fields to control that. All right, we've been talking a lot about polarization in terms of the machine. Let's see what happens when we actually take polarization to single photons. And this is an experiment you can do yourself. The idea is we take a laser and we have a polarization filter, like your sunglasses, if you got polarized sunglasses, right? That's a polarized filter. So it's going to send out, and we have a vertical selection. So it's only going to let vertical polarized light through and block everything else. And over here on the other side is the vertical filter, same thing, right? And we have a detector in here because my father is an optometrist and doesn't like people shining lasers into their eyes. So when I shoot out a photon, boom, boom, it doesn't get blocked by either. It passed this, now we know it's vertical. We pass that, it goes on. Simple. What about a more complicated case? I instead rotate it to horizontal polarization. So I filtered it this way. Oh, goodness. Boy, computers really don't know when people are on a roll, right? So I go to this point, and I've started it with a horizontal thing, but then I receive it with a vertical. What happens here? Bam! Stopped. Doesn't get to my eye, doesn't get to my detector. Now, a more interesting case happens when I tilt it slightly. Okay? In this case, I've started with a horizontal filter, so I know what's coming out is horizontally polarized light. But I'm going to give it a rotation of 45 degrees. What happens? We call this the diagonal state, and you'll see diagonal and then anti-diagonal is just rotated the other way. Right? So what happens here? Do I get half a photon because it's rotated half away? No, that's not allowed. Boom. Half the time it will pass, and the other half of the time it will get blocked. Remember, we can't have half photons, so the only thing left is half the time it blocks and half the time it doesn't. And it's random, 100% random. Remember that we want randomness for our quantum key distribution stuff. What happens if I do a more advanced device? Instead of blocking them, I put it through this beam splitter. Here, I'm making an anti-diagonal, and I take it and put it in the horizontal vertical. So I've swapped these two, and I've just used a different device that doesn't block. Whoops. Darn it. Lost my animation. Oh well. But it goes through, and half the time it'll go horizontal, half the time it'll be vertical. So I never get the right answer because it's random. I never know if it's anti-diagonal or diagonal because I only can see horizontal or vertical. So at this point, it might be good to remind ourselves of where we came from. But if there is a need for a small break, I don't. You want to keep going? Does anybody need a break?
Keep going.
Okay, good.
You're on a roll.
Okay, great. So let's get to the good stuff. Quantum key distribution, the specific algorithm that we're really interested in. Okay. Now here we have this is just what we started out with before. Alice has a key. They want to encode it and decode it again. And there's Eve, our eavesdropper. Infinitely patient, infinitely evil. All the money in the world, too. So the specific algorithm that we're going to talk about is called BB84. And the reason this is not the only quantum key distribution algorithm. The reason I like this is because it focuses mostly on polarization rather than exotic stuff like entanglement that I purposely didn't talk about in the quantum stuff. That was hard enough as it is, right? But there's an excellent book here by Ramona Wolf called Quantum Key Distribution and Introduction, and much of this explanation will come from that. Okay? BB84, B and B were Brassard and Bennett, I believe. Brassard, Bennett, something like that. 1984. So this is quite old technology. It still works. It's actually one of the most promising ones for satellite QKD. The idea is Alice. Wants to talk to Bob, of course. Alice creates two random bit sequences, really random. We're going to call them B and R. B for bits, meaning the data, R for rotation. B will decide if I'm going to use horizontal or vertical. R will decide whether or not I rotate it by 45 degrees, turning my horizontal and vertical to diagonal and anti-diagonal, right? The two interesting cases we just saw. So she makes this big long list, two big long list of numbers, right? She encodes the ones and zeros as horizontal and vertical, and you can see in this table here, right? Every time there's a 0 degree, a 1 is a vertical and a 0 is a horizontal, right? And every time it's 45 degrees, a 0 is diagonal and a 1 is anti-diagonal. Simple enough, right? Just a labeling change. She sends these photons in these two different random orientations. Remember, we can rotate it however we want with a Faraday rotator. And the intensity can be made as weak as we want. And the polarization can be in any direction that we want. She sends them to Bob. Now, Eve could, if she wanted to, intercept the photons. So she's allowed to do it. We've covered that. Bob, on the other hand, picks up the photons and randomly has decided to guess at a rotation that was used. He doesn't know. He's not coordinating yet, right? So Alice made some random polarization. Bob makes a guess. 50-50 guess, flip a coin. That's good cryptography. Flip a coin. Okay? And we're going to call that just R, but I call it S. R prime, as I call it guess here. Okay? Now, Bob is going to measure each photon to decide whether or not... that might be spelled wrong. Bob is going to measure each photon using his guess to decide whether or not to rotate. Okay? So he said, okay, I said it's going to be 0, 0, 0, 0, 45, 45, 45, rotated it by a little bit and stuff like that. And I'm going to use those guesses and I'm going to hook it up to a machine that detects horizontal and vertical and diagonal and anti-diagonal. Okay? So he's going to get some answers, ones and zeros. We don't know if they're right yet, though the coloring should help tell you. And he collects those things into a message, which he calls B prime, but this is just a measurement. And he announces that he's received the photons and how many he's received, which Eve could pick up, but mostly he's trying to talk to Alice. Hey, Alice, I got 2 billion photons, and here's, so what do I do next? Alice now tells the answer, the rotation answer, not the data. Just the rotation that was used. Did you rotate or did you not? Well, here's the ones. And Bob will collect all that and say, oh, these ones I got wrong and these ones I got right. So he tells her which of these he got wrong, which I've marked in red. The remainder must be correct. He must have guessed right. Good for Bob. Now, because Alice and Bob now know which ones were wrong, they can throw away. We'll never see those red answers ever again. We only keep the green ones. And both of them just throw it all away and don't care about rotations ever again, just keep the green data. Okay? So this was a great way because we said, well, there were random polarizations. Once you measured them, who cares whether or not Eve knows? And I'm just going to tell you which ones were right or not. We can take this and move this into a partial key. We're almost there. We've almost got an encryption key. And what we're going to do is we'll take the ones that worked, which is about half of them, and we're going to take a few more of them, and Bob is going to say, or Alice and Bob, doesn't really matter who says, we're going to say some of these I'm just going to use to see whether or not the quantum channel is too dirty to do anything with. And there'll be a reason for that in just a second. But they're going to take these things and half them again, and say we're only going to use half of them, and I'm going to tell the whole world which ones, because we won't use those for the key ever again. So let's say it's the first two. Bob says, I got a 0 and 1 in the first two. I'm not going to tell you what I got for the second one. No one ever hears about the second one. And Alice says, good news, you got a 100% success rate, proceed. At this point, we can do, that was the error estimation thing, and we can do what's called a privacy hash, which expands it back out. It's just basically sort of spreading out the code into a bigger number. That's all. Okay? And that's it. We take the remaining bits, and that becomes the key. Now, you notice I started out with 10 bits, 10 photons, 10 qubits, if you want to call them that. and I got back down to 2. So this is a very wasteful protocol, which is why we use it for keys, not for the whole message. We just use this to share encryption keys. It throws away a lot of information. BB84. The result, of course, is the secure key. So what could Eve do? We've been playing very nicely, haven't we? But Eve is in the middle, messing with things, watching infinitely patiently, though maybe she doesn't want you to know she's there. Well, Eve could capture photons in the middle of the process between Alice and Bob, that first round where those photons are sent. The rest of it is all just them talking in the clear. Only the photons was the first step. Those quantum photons. Now, she can't clone them because we said you can't do that. She could store them and release them later, but what good does that do for her? So she got the photons, she held them. You can hold photons in a big spool of fiber optic cable, actually, and you can delay them in time. She could store them, but eventually she has to release them or destroy them. All right? Now, if she stores them and moves them forward, Bob still gets the same answer that he always got. So Eve didn't learn any information. If she destroys them, she's messed up the whole thing. Bob says, I never got those photons, and they know Eve has been messing with the system. Eve could be a gopher that just bit on the fiber optic cable too, who knows. So Eve can destroy the channel, but she can't steal the information. She could measure them and send them back off, but the measurements are useless without Alice telling you which positions you got right. So you have to announce to Alice what you tried to use for her to tell you whether it was correct or not. Therefore, and this is made after the measurement is taken, the wave function is collapsed. Those 50-50 chances of saying it was diagonal, anti-diagonal, or it was horizontal, vertical, if you get it wrong, you get garbage data. So you've messed up that bit. And without Alice's set of the B's, right, the actual secret key, Eve can't rebuild the key. They can't rebuild the photons. So she can't copy the state. She can't take measurements that have any meaning. And even if she did, without the original binary data that Alice used, she can't fake it out. She can't spoof it. Now, Eve can disrupt the channel. She could spoof or jam Bob's initial guess announcement, in which case Alice keeps getting some wrong bits. That's why that error detection check was so important. At the very end, we threw away half the bits just to find out if someone's been stealing our bits. In this case, the keys don't match, and everybody gets garbage. But nobody ever gets to get the secret key without knowing it. No one can decode anything. So you've destroyed the process, but you haven't really snuck in anything. In fact, actually everyone knows Eve is out there now. The NSA is out there, right? Eve could also jam these confirmation announcements, but that's the same way. She's just messing with Bob now instead of messing with Alice. So Eve can't do very much in this protocol, all because we can't copy photons, and because if you guess wrong at those polarizations, then you get garbage. Eve can only disrupt or deny. She cannot manipulate or ever see the key. Let's look at a complete system. We're getting close. We're getting towards the end. I know I'm running long already. I'm sorry about that. Here's Alice and Bob, right? This is in pictures what I just said, but now we're seeing the equipment that we saw before. Alice and Bob's equipment. We're not going to deal with Eve anymore. Alice has a photon source, a mirror or a switch, which allows us to select whether we're going to use horizontal vertical or diagonal anti-diagonal. That's this first switch. Should I be up and down or 45 degrees? The second switch is whether or not it's a 0 or a 1. Okay? So this is the data here. This was the rotation. Those were our two random vectors that Alice started out with. Over here, and then they go through a telescope. The telescope is there to beam it through the air, right? That's your antenna. So in optics, an antenna is a telescope, right? Over here, I don't want to mess up my animation, so hopefully we'll get it right. But anyway, they send it through here. Bob receives this, and he has his random rotation going through a mirror or switch. He has decided the diagonal anti-diagonal or the horizontal and vertical. And then the beam splitter, which was just a set of filters that didn't block things, right? Remember the difference between a beam splitter and these filters, wherever I had them before, is that this always gives one answer. It never blocks. Okay, so I always get one of these eyes going on. If I use two filters, it could be that I put the wrong filter and I drop them both. Okay, so this is a little more efficient. And then the detectors, right? The single photon detectors. And lastly, we have a classical computer, or what we would think of as a non-quantum, just regular, plain old computer, maybe highly secure. And it's running the whole show. It's generating the random data. It's running the switches and everything like that. That's the boring stuff, right? Okay, so let's take a look at an example, life of a photon. We're starting with the first one that Alice has done, and she says the bit is 0, and the rotation is horizontal vertical, or what I call 0 degrees, right? So it's going to be up and down. And this is where you get to see what military-grade PowerPoint skills turn into. Here's the path. Ready? 3, 2, 1, go. Come on. Pew! Boom. The point is, Bob receives a 0 through the horizontal vertical path because Alice sent it through the horizontal vertical path using the 0 vertical, etc. Okay? So that was so much fun, let's do it again. Here's a 1. This time we're going to use the diagonal path, the anti-diagonal diagonal path. And there it goes, choosing this path instead. But it took the diagonal path this time. That was fun. What happens when we get it wrong? So this is the wrong guess. I'm going to send a 0 through the diagonal anti-diagonal path, but I'm going to pick it up on the horizontal vertical, meaning that Bob guessed this rotation wrong. So what happens? We don't know. Could be 1, could be 0. This is a garbage bit. And remember, it's garbage with 50%. Anytime I can turn a certain answer into a 50-50 coin flip, I've ruined anybody's guesses at trying to break my encryption. So this is effective. All right. That was the theoretical, technical, whatever. Let's take a look at the exciting stuff that's happening recently, which is real systems. And this is where I got involved with this at the University of Waterloo. I was not a QKD person. I was a quantum computing person, so this is not my area of expertise. Just call me an enthusiastic amateur. This paper right here, which is an excellent read, is a good summary of all of the stuff that I've talked about in the context of putting it all into space. And on the ground, of course, you need a ground segment, right? But the point is, recently, there have been 3 satellites sent out. 2 from China and 1 from Japan. I can't remember which ones it was. Misius was a Chinese satellite to demonstrate QKD. It did not use the technique that I was talking about. It used an entangling technique. But this one is considered very reliable. So this was a successful system by China. Tiangong 2 was a space station payload that hosted a compact QKD system, and it successfully performed this up and down into space. I believe this did use BB-84. Jinan 1 is a dedicated QKD satellite, just like Misius was. And it's designed to build a whole network. So this is satellites talking to each other and kind of building a bigger and broader system than just Misius, which was just to do the kind of proof of concept. There are 5 planned things, and this is a very recent paper. This was done just at the beginning of April. 5 different new satellites being deployed by the US, by Canada, by the European Space Agency, 2 by IRIS, and this one here, the Canadian system, which we'll see in just a second. Okay? So this is a great assessment of all sorts of parameters, including things like, what colors of light should we use, and whether or not we should use low Earth orbit or high or medium or high. The answer is low Earth orbit, by the way, because you want to be close enough that the beam doesn't spread out. Otherwise, I lose photons. As I shoot a beam, even a laser beam off into space, it spreads out, which means that unless I have a hugely wide satellite, maybe kilometers wide, I would have to miss a lot of photons. But if I put them in low Earth orbit, I have a better chance of hitting my target. So I don't miss as many, because we lose a lot, right? We lose 4 of them in BB-84. Okay, this is the Canadian system. This is being driven by the University of Waterloo and the University of Toronto. It's called QEY-SAT. I can't figure out how you do this. This is the concept view of the payload itself, the optical system, the photomultiplier too. It's actually, this is the telescope up here, motors, and a few other things like that. The concept of the system is actually to link two satellites together across Canada using trusted, very important, trusted satellites. We trust the satellites. It's not an intermediate system. Oops. Sorry, I thought it was my alarm. I'm running very long. This is a plot, by the way, of the color. This is atmospheric attenuation. These big dips mean that these are wavelengths that we can't use because the atmosphere eats it up. So if anyone was wondering, why is the sky blue? Now you know, it's the dip. Okay, but there's a huge dip. And the interesting thing, and this is really kind of cool, is the wavelengths that are acceptable, that don't attenuate very much, happen to be telecom wavelengths. 850 nanometer, 695, 1550. These are all things we have lots and lots of technology for fiber optic already. Okay? The timeline, which is, I admit, is very hard to see, but we're basically expecting this launch to happen in 2025. Okay? But there's more. We can do it with planes. And the reason I was interested in this is because they use a Twin Otter, which is a great plane to jump out of. So the demonstration platform was not to use a satellite, but to use a plane to simulate the satellite to see if it works in just the regular atmosphere. Right? This is another Waterloo group. These are the receivers. It's complicated, but it's not really all that different than the schematic cartoon that I just had. The wavelengths are 850, 795 for the uplink and downlink. The classical channel is over here, and the quantum channel, I believe, is, quantum channel's on the top, classical channel's on the bottom. And then this one, I believe, is the ground segment, 795 and 850. So visible light. So the plane flew two paths. It flew an arc, about 7 kilometers, and then it flew a straight line. They were roughly 3 kilometers of downrange. So that was the line that they were doing. This is the machine. This is all from this paper by Chris Poe. And this is the actual thing inside the plane. It looks like a big telescope with a bunch of stuff on there. That's why we call it a telescope, because it looks like a giant telescope. And this is the ground segment, right? So we've got a kind of a support truck. And then the actual transmitter is on this, this sort of tripod-looking thing. And I think this is housing the laser in this red thing, if I'm not mistaken. So high altitude platform. Okay, thanks for being with me through all that stuff. In summary, cryptography depends so heavily on the key that its delivery must be secure. You got to get that first key in there. You got to deal with the fact that sometimes people will steal or compromise your key, or you got to reboot it. And how do you get another one? In space, while no one can hear you scream, that also means you cannot call for a new key. Internet-based systems like PKI are not sufficient because that root of trust eventually stopped when you can't reload the operating system to get a new set of root keys. So new things have to work for satellites. Quantum effects, especially single polarized photons, can never be copied or examined without destroying information. And QKD protocols like BB84 allow the exchange of this small data, which we will use as a key, even though there's a presence of eavesdroppers, because Eve can do nothing but destroy data. She can never see it, though, or manipulate it, by the way. She can't fake data. And satellite QKD has been demonstrated on several satellites, with more coming on the way. So with that, thank you so much for your time, and I'm happy to take any questions that you have.
So I'm sure Rich would be happy to take any questions.
You might have answered this already, but what stops Eve pretending to be Bob?
So that's a great question. In the process of, there is nothing to stop Eve from pretending to be Bob. There is nothing to stop Eve from pretending to be Alice. The problem is, all they've done is loaded a key that Alice will never generate data for. right? So Alice may think she's talking to Bob and she's talking to Eve, but because she has not given the correct key to Bob, Eve could see bad data. Eve can encrypt bad data. Bob could encrypt bad data, and the man in the middle can't actually occur. So I'm not sure if I answered that correctly. It's a little circular. But man-in-the-middle attacks have another more dastardly way, and it has to do with when those double photons occur. That Eve can't actually get a copy if two photons were generated at the same time. And that's a much more dastardly thing because she can be invisible at that point. Yep?
Is it one photon per bit? Is there any sort of...
4 photons, actually.
per the final bit, but I guess because I don't have a perspective of how accurately you can aim these, it seems kind of mind-blowing that you can send 1 photon and that's definitely received. You know, can you talk a bit about how accurate that is?
The key loss rate is very high. So you might send 1 million photons and get 10% of them. Just through loss channels and stuff like that, right? It gets there are lots of atmospheric effects that reabsorb it. It's actually worse in fiber optic cable, where the light can interact and get attenuated to the within the fiber itself. And remember, attenuation in our world just means reducing the energy, changing the frequency, or just simply absorbing the photon. So this is a high loss type of thing, which is why we reserve it for keys rather than the actual message data. Once we have the key, we will use in our satellite system an AES encryption or Diffie-Hellman protocols, anything you'd like. Yep. Power.
Yes.
How much? Never enough. I would have to look at the actual details of those papers. I can get with you afterwards because I have a printout of it. But it's on the order of a few tens of watts for the LEO ones. Because we actually don't want a lot of power. Remember, a lot of power means a lot of photons, right? So what we're saying is, if I have high power, like a KU band transmitter might be 100 watts, for example. That wouldn't be unusual, or even a kilowatt. That means I'm getting so many photons happening so fast that I actually can't filter them out. So the received power levels is very close to that minus 174 dBm threshold of thermal noise.
But again, in tandem, you're challenged with your error rates as well.
You are, yeah. So repetition. The QKD demonstrator from Waterloo was doing about 100 kilobits of delivery per second, and that's at a generation rate that was into the gigahertz range. So they were losing a lot.
Is it a proof of concept that still needs...
Yes, very much so. Most of those technical things are about the signal-to-noise ratio of the detector. That's why we talked about what's a low noise and what's not and stuff like that. But cryogenic things and stuff like that, too.
So what's the difference in efficiency between, say, BB84 and entanglement?
So an entanglement protocol, I would have to honestly look that up. They're comparable. I believe the entanglement protocols have higher key rates, but are less practical in the actual environment. And it turns out that, I can give you the review paper here, that the practical concerns tend to lend themselves towards the things that BB84 is good at rather than the entanglement ones. But yeah.
What's the distance limitation?
So LEO, there isn't really a distance limitation for the photon. What it really is about how well you can pick it up. Right? So how big is the lens on your satellite to pick up this wide thing? Because a photon going through outer space, like cosmic rays, they stay around for billions of years. So the real question is, did the one photon get absorbed or not? And that turns out to not be a distance thing, not at these wavelengths where the atmosphere is fairly transparent.
So you could have two situations. You could have communication between the Earth and the Moon, Earth and Mars.
Yeah. In satellite, it does have to be line of sight, right? Obviously, we can't block it and stuff like that. But the Waterloo concept with the 2 satellite was there to try to, QISat is about trying to build a full quantum internet. They want to surround the whole world with this stuff. So, yeah.
can ask?
Yep.
So say a certain radio club wanted to, do a demo across a room or something. How feasible is that?
How many millions of dollars will that cost? Most of those things are $1 to $2 million platforms. Not so much because it's because the good quality optics are expensive. One of those Hamamatsu photomultiplier tubes is $60,000. A laser is $250,000, and things like that. And the platform, the vibration stabilization and stuff like that. So it would be difficult to do a full QKD demo. But the basic things about polarization and stuff like that, those are fairly straightforward things. You can do them with laser pointers and stuff like that. You can buy the single photon detectors for $500 at Thor Labs and stuff like that. So and polarization things. It's just the full system to get performance. That's where the money is in. Yeah.
Towards the end there, you showed the ground station and the telescope thing. How much smaller is that going to be when it goes into space?
So these are going to be CubeSat type of things. And again, this is not my area of expertise, so I don't want too much to speculate. But generally, a CubeSat, 50 mil on a side sometimes, maybe smaller, sometimes as small as 10 mil on a side and stuff. But I think that one's probably going to be, a couple shoe boxes. Okay. Yeah. For the space segment, the ground segment is it can be that usually has a really big mirror too because,
So I have a question. So for this, so in your presentation, you have illustrated how the decode and encode and decode and how it can be, how effective when it is to avoid the information packet.
Yeah.
That is about encoding and decoding.
Yeah.
So the problem is, for we say that we based on the photonic technology to transmit data as a kind of high frequency radios. The problem is, so when in a very noisy channels, or some people want to block the data, don't want to receive that data.
Yep.
So in that case, how to, for example, to avoid such kind of things?
Yeah. So the step now you gotta walk back all these slides and stuff, right? Come on, there. So this error estimation phase tells us whether or not we got a good match or not. And this will fail many times. This is not a particularly robust protocol because in the case where eavesdrops or the photon is lost because of misalignment or whatever, we just simply get we get fewer. And we just accept that. And eventually we say, how many errors did I get? Remember that second half of the things that I threw away just for estimating the channel was to decide whether or not I got enough to work with. So this is a very lossy process. Again, this is why we only use it for rebuilding the keys. And once we have the key, we use regular encryption. That can be eavesdrop, but it's already encrypted. So who cares? They just eavesdrop on garbage or encrypted data. I think there was a question here.
I was just wondering, you mentioned about the Chinese satellite, one of them that used encryption. Was that something that they announced, or it was determined by eavesdropping?
No, this was publicly announced.
Oh.
Yeah, there's textbooks written about the success of the project. And like most of these satellite platforms, they're actually not just trying to do QKD. These are also, what does teleportation look like? Can I teleport information up, through the world, up to space? Can I move things with entangled protocols and stuff like that? So these are also doing general quantum optics or photonics problems as well. So in Misius, for example, they were very proud to show the long-range entanglement, and QKD was a natural thing to do as long. So the expense of these things makes them multi-mission platforms to work with.
Okay, if there are no more questions, I'm sure Rich would be happy to chat with anybody following the talk. He's very knowledgeable. You can talk to him about almost anything and he'll be an expert in it. Yeah, it's getting me to shut up is the problem. But I'd just like to thank Rich again for a super interesting talk.
Thanks, everybody.